class. In this video, I'm going to introduce you to some of the most common logic functions. So the first one we're going to look at is the AND function. Mathematically, this is represented with multiplication. The output in any row is a 1 only when all inputs are 1s. This is what a 2-input AND gate looks like. Notice how we have this straight vertical front. The output here would be A times B. Now, because we have two inputs, A and B, and each of those inputs can be either a 0 or a 1, we have 2 squared or 4 input conditions. And so this will correspond to 4 rows in a truth table. So here I've set up a truth table for this gate. So for A, I have used the following pattern, 2 zeros, 2 ones. And for B, the pattern 0, 1, 0, 1. And if you do this, you'll get all 4 possibilities. You see, this first one corresponds to both zeros. The second one, A is 0 and B is 1. Then we have A is 1 and B is 0. And finally, both A and B are 1s. Now we can form the output column A times B. So we simply multiply these numbers together. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. This would be a drawing of the 3-input AND gate. The output is A times B times C. Now, because there are 3 inputs, and each can be either a 0 or a 1, we have 2 cubed or 8 possibilities. Here is the corresponding truth table. So to get all 8 possibilities here, I used the following pattern. 4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, and then 0, 1, 0, 1, 0, 1, 0, 1. When you set that up properly, it corresponds to counting from 0 through 7 in octal. If you look at your conversion charts from your previous lesson, you'll see that this is the same as the octal binary conversion chart. Okay, so please use the pattern to establish your inputs. And then A times B times C will have an output that looks like this. We're only going to have a 1 when we have all 1s here. Everywhere else we will have a 0. So this corresponds to 3 series switches. So here are switches A, B, and C. How would we get the current to flow from this point to this point? The current would only flow when all 3 of these switches are closed. Otherwise, it would be interrupted. So when all 3 switches are closed, the current will flow. And that would correspond to this last possibility here. When all 3 are closed, the current can flow. If one or more switch is open, the current will not flow, and that would be represented by these other states here. Okay, so that's the AND function, and now let's contrast that with the OR function. So this is what an OR gate looks like. So it's round in the front is the key. It's a little tapered at the end as well, but the most important thing for me is that you would draw the front round instead of straight and vertical like an AND gate, okay? So we need this round front. So here is the 2-input OR gate. The output is A plus B. So now the difference is the output will be a 1 when any one of the inputs is a 1. So if you have at least 1, 1, you will have an output of 1. Okay, so use the pattern for A and for B, and now we're adding. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is also 1. Okay, so we get a 1 everywhere here except in the top row where we had only zeros. So here's the 3-input OR gate. The output is A plus B plus C. Use the pattern to establish A, B, and C. And now for the output here, only in the top row where we have no ones will we have an output of 0. Everywhere else, the output will be a 1. Okay, this would correspond to 3 switches labeled A, B, and C connected in parallel. So how can you get the current to flow from this point to this point? The current will flow in all possibilities except for this one depicted. This would correspond to the first row here in our truth table where all switches are open. That is the only way that the current will not flow from this point to this point. If only one switch is closed, for example, if A were closed, the current would take that path. If a couple of switches are closed, the current certainly can flow from left to right. And when all 3 are closed, which would correspond to this last possibility, certainly the current can flow. Okay, let's move on to the last page. Here at the top, I've drawn an inverter. So this is symbolically what an inverter looks like. Mathematically, it's the complement of the input. So we call this the NOT function. So if the input is A, the output is A naught. Or you can call it A bar or A inverted. So A itself can either be a 0 or a 1. What will A naught be? Its opposite, so a 1 and a 0. Okay, so that's the NOT function. And then I've shown NAND next. So NAND begins with an AND gate, and then there's a little circle on the end of that AND gate. And this circle takes the place of a full inverter. So it's as though you have an AND gate and then an inverter. So the output is not A times B, but A times B all inverted. So let's look at just the truth table for this gate. So set up A, set up B. Now we do A times B, and that would be 0, 0, 0, 1. And now, because of the circle here, we invert that product, and that will give us an output of the opposite. So 1, 1, 1, 0, like this. Okay, and the last one for this course that we're going to look at is the NOR function. So this is equivalent to first an OR gate and then an inverter. And so here we have OR drawn, and you can see again, the only difference is there's a circle attached at the back of the OR gate. So the output is A plus B all inverted. So we finish our lesson now with the corresponding truth table for that. So we set up our 4 possible input conditions, And by the way, this is like counting from 0 through 3. 0, 1, 2, 3, right? Because this is obviously 0. This one would be 1 times 2 to the 0, which is 1. This would be 0 plus 1 times 2 to the 1, which is 2. And this last one would be 1 times 2 to the 0 plus 1 times 2 to the 1, or 1 plus 2, which is 3. So anyway, just showing you that this too is counting. However, more importantly, since we're talking about NOR, once we have this established using the pattern, we add. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 1. Okay, so this is Boolean adding. And now that we've got, this would be for our OR gate. And then because of the 0 here, we actually want one more column for NOR. And we take the opposite of this column here, which will be 1, 0, 0, 0. Okay, so I hope that makes sense to you. This document is posted for you in Blackboard. And you're now ready to watch the next video, which will be actually writing the Boolean expression for some circuit drawings, and then taking some Boolean expressions and trying to draw the corresponding circuit diagrams. Okay, thanks a lot. Have a great day.